We're very happy to have Alex to tell us something about annular symplectic Khovanov cohomology. Thank you.
Okay, so thank you for the invitation. So I don't really know what people know, and this is not exactly what I'm thinking about right now. So I will try and be only moderately incoherent. So I'm a symplectic person, but this story has kind of three contexts or motivations, depending on which part of mathematics or physics you're in. They might seem differently compelling, and I'll try and explain why, if you start from any of these points of view, there's some interesting story around. So the first is, can we understand Khovanov's kind of combinatorial invariant of links geometrically? Maybe I should clarify that to me that really means symplectic geometrically. Yeah. And this was something that Khovanov asked in his very first paper on Khovanov homology. He asked, is Khovanov homology somehow a Floer theory? The second context is a kind of purely symplectic question. So if E is a quasi-projective, for instance, an affine surface, so by surface I mean a real four manifold, a complex algebraic surface, well then there are these God-given moduli spaces of points in E, the Hilbert schemes. So can we understand the symplectic topology of the Hilbert schemes of n points in E? So we sort of imagine that E is some accessible four manifold, and there are these higher dimensional manifolds, and we would like to understand something about those. And then the third broad setting starts from a classical result in Kähler geometry. So Deligne, Griffiths, Morgan, and Sullivan proved classically that the cochains on a Kähler manifold are formal over the reals. Okay, so what this formality means is that various secondary operations in the cohomology of a Kähler manifold, things related to Massey products, vanish, and they vanish kind of universally. They vanish for consistent reasons. Okay, so formally, this is a differential graded algebra, and it's equivalent, isomorphic in the category of differential graded algebras to cohomology with the zero differential. And one can look for a complexification of this statement in the landscape of hyperkähler geometry. So if X is actually hyperkähler, well, cochains on X are already formal. There's no more to be said. But one can consider configurations of complex Lagrangian submanifolds. And then one can ask the question whether or not the natural Floer theoretic invariant, which is the Floer cohomology of these objects, is this formal now as an A infinity algebra over the reals. So I sort of think of this as a kind of complexification of the classic formality of Kähler manifolds. So, I mean, if these are complex Lagrangian, then there are a circle of symplectic forms, and Floer cohomology is kind of deformation invariant. So you can take any in the symplectic forms in the circle for which they're canonically Lagrangian. Okay, and so these three stories, which I think maybe appeal to mathematicians in different areas, come together in studying one particular class of examples, which you might have come to by kind of thinking about any one of them. And that's sort of what I want to talk about. So I'll start with some kind of knot and braid theory in symplectic topology. Okay, so a braid on D strings is a loop in configuration space of D points. So here's a braid on 4 strings. And we can always turn it by an operation called knot closure into a knot in which we take the same braid, we multiply it by a trivial braid, and then we form a knot by capping it off top and bottom, as in this picture. Sometimes call this kappa of beta. And this is a sort of efficient way of presenting knots from 2 points of view. So it's a classical fact that every knot is such a braid closure and the deeper fact due to Markov, first proof was probably written by Joan Berman, that 2 braids lead to the same knot if they're related by explicit known moves called the Markov moves, one of which conjugates a braid that doesn't change the number of strings, and the other of which takes a braid in the D string braid group and sort of half twists in a twist on one additional strand. So this is in the D+1 string braid group. So here, if beta has D strings, then you're sort of twisting in with the half twist on the D and D plus first strings, either positively or negatively. Okay, so this will be our input into thinking about braids. And if you're a symplectic topologist thinking about braids, the natural thing to look for is a symplectic fiber bundle over the configuration space of D points in R2. So the fiber is some symplectic manifold, and the structure group of this fibration is meant to be the group of symplectomorphisms x omega. So then if beta is a loop in the base, we get an induced sort of phi sub beta, which is a symplectomorphism from X to X. And there are then two standard ways of extracting some sort of invariant in symplectic topology. So one is to take the Floer cohomology of phi beta, and the other is to take the Floer cohomology of L, phi beta of L, where L in X is some chosen Lagrangian submanifold. And one of these is somehow very closely related to the other, the Floer cohomology of a simplex homomorphism. You can think of as the Floer cohomology of the diagonal and the graph of phi computed in X times X.
So conceptually, how should I think about these two guys? First one contains more information.
They contain different information. I mean, this is generated by fixed points of phi. This is generated by intersection points of L and phi L, which, they're, but they're not somehow just the fixed points of phi that happen to lie on L, right? So that the generators of these two complexes are somehow neither one contained in the other. Traditionally, this was used to extract dynamical information in symplectic topology because it's generated by fixed points of a map. This was used to study the topology of Lagrangian submanifolds viewed as some object of interest in their own right. Any other questions at the moment?
But the first is the right-hand side definition.
No. So the right-hand side is a kind of non-trivial but not especially hard theorem depending on your context. So yeah, let me say a word about the definitions of. Sorry. Of these two. So fixed point Floer cohomology, this is generated by fixed points of phi. Okay, and so there's some general assumption that they're non-degenerate, and if your manifold is non-compact, you'll need to think a little bit about fixed points at infinity. And the differential, well, we form from phi the mapping torus. So x times 0,1 modulo the relation that x1 is related to phi x0. So, and we think of the mapping torus as lying over a circle in C star. So we have some fibration with fiber x, but as I go around the loop in C star, I come back by the monodromy phi. Okay. And so we build the mapping torus times R, which naturally maps down to C star. So let's call this total thing P phi. And now the fixed points of phi define sort of orbits that lie either near 0 or near infinity in this mapping torus. And the differential in the cochain complex counts holomorphic sections of this map, which are asymptotic to loops that arise from fixed points. So now, of course, fixed points of phi as a set are, naturally the same as intersections of the diagonal and the graph of phi. But, and the identification of this, cohomology group with Lagrangian Floer cohomology for this pair of Lagrangians involves kind of argument that takes a strip with boundary on the Lagrangian and the graph and kind of folds it over. So you glue this boundary arc to this boundary arc via the map, the identity times phi. And that turns a strip into a cylinder with two punctures that you could interpret in this landscape. Yeah. That I hope I'll talk about. I mean, it's related to annular Khovanov homology. But this is a lower tech theory because this counts holomorphic cylinders, so there's no codimension 1 bubbling. So this is defined unproblematically in cases where Lagrangian Floer homology would only be defined problematically, which is why it's useful to separate out the two definitions. And yeah, they have slightly different interpretations in the sort of algebra when one passes to Fukaya categories. Okay, so one way of interpreting Khovanov's question from his first paper is the Khovanov homology of a braid, which, for reasons that will become apparent, the Khovanov homology of the knot closure of a braid equal to Floer cohomology of something in either of these flavors. And we know something about this, but we don't know as much as we'd like. But you're somehow not going to guess the answer just randomly. So it's useful to have a particular definition of Khovanov homology in mind to get anywhere, which involves something called the arc algebras. So these are due to Khovanov. They're diagrammatic algebras. And they're based on the crossingless matchings on two endpoints. So one such thing is a diagram of n arcs joining two endpoints, n pairwise non-intersecting arcs in the upper half plane. So here are some examples for n equals 3. And Khovanov defines an algebra, the arc algebra on n or 2n strings, so it's going to be a direct sum over pairs of crossingless matchings P and P prime of some sort of graded morphism group between the crossingless matching associated to P and the crossingless matching associated to P prime. And what is this thing for a particular pair of matchings? This is given by taking one of them, reflecting the other in the horizontal axis and putting it next to it. Now I get an unlink of some number of components, a collection of planar circles. And this piece of the algebra is given by the cohomology of S2 to the number of circles I see in this picture. So in this case, I would get H star S2 tensor H star S2. And then I need to tell you how to multiply in this algebra. So now I have kind of 3 of these matchings, and I'm trying to write down something that looks like this. And well, I take, my first matching. This is rho. I'll then take the thing that was rho prime, but I'll actually have that twice. And then I'll have whatever rho double prime was. So I have a copy of H star S2 to some number of factors here. And I have a copy of H star S2 to some numbers of factors here. And I need some map. But the observation is that whenever you have one of these crossingless matchings and itself arranged in this way, well, then there's a kind of canonical cobordism between them, in which I just take matching arcs and I imagine opening them up and gluing them together. And even if I hadn't started with the one that was just a product of parallel circles, whenever I have a matching in itself reflected, there's a canonical such cobordism. Okay? So if I have some sort of cobordism induced maps on copies of H star S2, then I'll win. And so what I use is the TQFT associated to the Frobenius algebra H star S2. So in other words, if you've met Khovanov homology before, this is kind of the standard picture that arises when writing down maps in Khovanov homology in the usual sort of diagrammatic approach. And Khovanov showed that, well, my favorite object is this one. So let me call this rho 0.
Sorry, sure. So you want this to be a compensation, so it's like
exactly. So there's a cobordism here in which I'm attaching 3 handles. Okay, and so what I'm going to do is take the induced cobordism map for those 3 cobordisms, and the order of them won't matter whenever I have a crossingless matching and its reflection.
I thought that you have a cobordism. The initial part is like the disjoint union of these 2 pictures, and the final picture is like you erase the middle guy, just concatenate the very top.
Sorry, you're exactly right. I should have said this is going to, as here, rho double prime, and this is on this. Excellent. Thank you. Yeah, exactly. And this is the induced cobordism map from this cobordism, which at the end is just landing in the thing that you associate to the planar unc-link associated to rho and rho double prime. Exactly. Thank you. Sorry. So the facts that Khovanov proves are, first of all, that the derived category of modules over this resulting algebra has an action of the break group on 2n strings. And secondly, that if beta is a braid on n strings, then the usual Khovanov homology of the knot closure of beta is given by x in this derived category between the module associated to my favorite object and its image under the thing associated to the 2n strand braid beta times the identity. So in other words, if you just start with the diagrammatic definition of Khovanov homology and you're not kind of very wise and you're looking for a symplectic interpretation, I think it's very hard to know where to proceed. But this was kind of Khovanov's second definition of Khovanov homology, and it involves a category with an action of a braid group and something that's a morphism group in that category associated to some kind of preferred object and one of the braid group automorphisms. Okay? And this is very much the kind of structure that we're very used to seeing in symplectic topology, okay? Where we would associate to a symplectic manifold its Fukaya category, symplectomorphisms would act, and morphisms in the Fukaya category between some object and its image, this is the kind of bread and butter of Lagrangian Floer homology.
So I read the first paper, but not the second. How do you prove that this definition, the definition from the first paper and this one are the same, or prove that equality there?
Yeah, so in some sense, what he proves is that, I mean, when you construct the braid group, you see you have exactly the canonical skein exact triangle. The braid group action is defined by forcing the groups that you get to have canonical skein exact triangles. And starting from there, it's not so hard to see that it must be the same as Khovanov's theory. But I mean, yeah. So in fact, the reason that Khovanov gave this reformulation is that in this language, it's very easy to describe invariants associated to tangles rather than just knots as bimodules over the derived category of an arc algebra on one number of points and another number of points. So what he actually does is build a functor-valued invariant of tangles in this second paper, and then observes that the structure recovers the original definition in the case of tangles with no endpoints. Okay, so there's a short digression to introduce the symplectic manifold we're going to care about. The A Milnor fiber is this symplectic manifold. It's a quasi-projective surface where this is a degree n polynomial with distinct roots. And if I call this X sub P, then there's clearly a family over the configuration space of n points in C, whose fiber at a point corresponding to the roots of P, which are indeed some unordered collection of points in C, is this space X sub P. So being the fiber of a symplectic fiber bundle, this comes with a natural action of the braid group. This is not quite the space we want. We want something a little bit more complicated. But let's just note that projection to the Z plane defines this nice structure on X sub P. We have the roots of P. At a root of P, the fiber of this projection map, x squared plus y squared is 0, is just a singular conic. So union of two planes. At a general point of C, the fiber is a copy of C star, x squared plus y squared is some random value epsilon, and a path gamma between two of the critical values defines by kind of now rather classical construction of Donaldson, a Lagrangian two-sphere in the total space of X sub P. So this is given by thinking about the kind of natural real circle in C star. If you think about this as T star S1, the sort of equator, tracing it out over this arc gamma and having this equator shrink just to a point at the ends. Okay, so paths gamma between pairs of critical points give rise to Lagrangian S2s in my four manifold. And Khovanov's construction made essential use, as I've laid it out, of a picture which involves having three arcs joining 6 points, or more generally, n arcs joining two endpoints. So this sort of picture of a collection of nested arcs defines a Lagrangian, which is a disjoint union of n copies of S2 inside X sub P. And, as we'll explain a bit later in the talk, you can develop the theory starting from this, but sort of historically and conceptually, it's nonetheless better, at least initially, to replace this by the product of these arcs. So if I call these arcs gamma 1 down to gamma n, we take the product, which is now a Lagrangian S2 to the n, and this naturally lives inside the Hilbert scheme of n points of xp. And in fact, it lives inside what I know Peng refers to as the horizontal Hilbert scheme. So this is an open subset where the subscheme projects via pi nicely to C, where pi is the induced map coming from X sub P. So if you don't know or like Hilbert schemes, let me just say that this is very close to just the symmetric product of n copies of xp. But we resolve its singularities. To get something smooth, because symplectic topology, and in particular Floer theory, is not good at dealing with singular symplectic manifolds at the current development of the subject.
Question.
Yeah.
So if I just take just one strand setting n equals to 1, just looking at this single copy, sorry, not n equals to 1, still Annular fiber, just not doing the cube, just doing this thing, and I do this braiding things. And what do I lose? What information I do see?
Sorry, are you saying if I take my basic Lagrangian to be this and apply the break group and try and take Floer homology, or?
I guess if I'm not sophisticated enough,
Sure.
Just looking at this Annular fiber, I see many similar points of very heavy and bringing them around.
Absolutely.
And I could have Henry on it.
Absolutely. So you can certainly study invariance of braids by taking Floer homology of symplectic morphisms of the Milnor fiber, or just picking some Lagrangian. I don't think anything is quite God-given here, but you can just pick, you know, this one, say, and think about Floer homology of it and its image. I don't know any way to extract a really interesting not invariant, but you'll get interesting invariance of braids. You won't get Khovanov homology.
I see. Okay.
So if, I mean, this is of course an easier theory, and you can, for instance, extract the Alexander polynomial because you can extract the Barrow representation. So there's non-trivial content to just working with, you know, Floer homology on the Milnor fiber. But I don't know how to get, you know, I mean, you know, I was setting out to try and recover this because then I would know I got Khovanov homology thanks to the work Khovanov had done, rather than setting out to just study invariance of braids.
Okay, great, thanks.
Any other questions? So I have no idea what people know. Is this kind of in any sense comprehensible? Yeah, of course it's good for you. You work on this stuff. I mean, if you're the only person who dares answer, that's kind of horrifying, but never mind. Okay, so in this space, so the Hilbert scheme of n points in this xp, where degree p has 2n, and I pass to this open subset, so that's all a mouthful, so I'm just going to call this space, you know, y2n. Well, we actually have, you know, a Lagrangian sort of L row diffeomorphic to S2 to the n for each crossingless matching. There was nothing special about this one I singled out. So just remember, I've got my 2n points. I take some collection of arcs that joins them in pairs. Each of these arcs defines some copy of S2 inside the four-dimensional Milnor fiber. I take their product. The fact that that product lies far from the diagonal means that it both lifts to the Hilbert scheme and lands in this nice open subset that I haven't quite specified that defines this space Y2n. So then, using just kind of basics of Floer theory, I get an A infinity algebra direct sum over pairs of crossingless matchings of the Floer cohomology of LP and LP prime. So this is computing in Y2n. So maybe I should just make a small remark for people who don't think about this. So in Lagrangian Floer cohomology, I write down a complex which is generated by the intersection points of L and L prime, at least if L and L prime meet transversely. and there's a differential on this complex which is defined as in Morse theory by giving its kind of matrix coefficient. So the boundary of some intersection point is some sum of numbers of moduli spaces times y over different other intersection points y. Okay. And here mxy is a space of maps from the strip R times 0, 1 to your symplectic manifold X. They should be holomorphic for some complex structure J. They should asymptote at one end to X and the other end to Y. The boundaries should lie on your pair of Lagrangians L and L prime. And we actually count these modulo some reparameterization. So these are the morphism groups in a category associated to X. So we have the Fukaya category of X, in which the objects, roughly speaking, are Lagrangians, and the morphisms from L to L prime are either CF of L prime or HF of L prime, depending on how much algebra you're hiding. So then you need to be able to compose morphisms. So composition counts triangles. Well,
In the vanilla category, yeah.
I mean, you know, every A infinity category has a minimal model, so it's quasi-equivalent to a category in which the morphism groups are actually the cohomologies of the chain complexes. This tends to be kind of much more, you know, first of all, this is intrinsic to L and L prime, not depending on their Hamiltonian position. This is typically a much more manageable thing. But it's true that usually when you define the Fukaya category, you know, you take that to be the definition. But,
and the existence of these minimum models, is that something, or?
Yeah, it's purely algebraic, and you can build the minimal model by a kind of explicit procedure involving counts over trees. Yeah, so it's a concrete form of homological perturbation. You need to be a little bit careful if you're working over a ring that's not a field, because the usual algorithms involve splitting the map from chains to cohomology non-canonically, and then using those cocycle representatives, splitting the map from cocycles to homology non-canonically, which you can always do over a field. There are results for minimal models over more general rings, but they take, you know, they're not as universal.
So in this case, just compute your compute the elements of the algebra, differentialize.
So I'll come to this. I'm going to talk, you know, the rest of the talk will be an informal talk on formality. So the composition in Floer theory, if I have a morphism between L and L prime, and I have a morphism between L prime and L double prime, well, then I should be able to extract a coefficient, which is some intersection point between L and L double prime, and this counts holomorphic triangles with boundary that looks a bit like this. But in the category composition's associative, and you come to try and prove this is associative, and what you find is that you need to think about moduli spaces of holomorphic quadrilaterals. And then you quickly realize that this algebra, of course, has associated operations that count holomorphic n-gons for any n. And so the collection of these operations equips the structure CFL, L, or for a collection of Lagrangians, the sort of total morphism algebra with this structure that's known as an A infinity structure. Let me write it at the cohomological level. Okay, so as well as a product, which is called mu2, which is a map from A tensor A to A, there's a mu3, a mu4, a mu5, etc. This inputs, mu k inputs a k tuple of elements of the algebra, and it outputs something in the algebra in some shifted degree, shifted by 2 minus k, and then there's some quadratic relation of the form that if you compose these in all possible ways for k inputs using two of the operations mu I and mu j, such that the total number of things they would eat is k, then a signed sum of these things is 0. Okay, so we have this whenever we have a collection of Lagrangians in any symplectic manifold up to some technicalities in the basics of Floer theory for, Floer theory just being well defined, but in nice, say, affine varieties like the one we're working in, and some sort of, simply connected Lagrangians, which these are, they're products of S2s, you always get an A infinity algebra. Yeah. 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 Yeah, I mean, so the A infinity, I mean, the Fukaya category is just, looking at this over all possible Lagrangians. Right. So this contains all the information in this case. I mean, you need to be careful because you're in something non-compact. So compact Lagrangians never generate the Fukaya category of a non-compact manifold in an interesting way. But this is actually a Stein manifold. It retracts to a compact core, and the compact core is indexed. I mean, the union of these L rows is close to the compact core. Okay, so if we want to compare to Khovanov homology, we have now two goals, two immediate goals, right? If we want the derived category of modules over this arc algebra to resemble in some way the derived category of modules over this Floer algebra, okay, which, sits inside the derived Fukaya category of this space as a kind of natural piece of it, okay, so it's sort of somehow symplectically natural, then we need two things. The first is we just need the algebras to be the same. But when Khovanov built his story, he just had an algebra, right? There wasn't anything else. It was just an algebra. But this is an A infinity algebra, okay? And the A infinity, an A infinity algebra is not just an algebra, and that's going to change what happens when you try and make computations in this thing. So we need A2n to be formal. In other words, quasi-isomorphic to its cohomology, which is somehow the same algebra, but with all the higher differentials set to 0. So, and secretly, we would need this equivalence to also entwine the braid group actions. I told you that Khovanov built a braid group action on this, and this comes, for rather general reasons to do with the fact that this Fukaya category has a braid group action with a braid group action. So, and both of these are kind of extremely hard. So, so it's a theorem due to Mohammed Abuzaid and myself from some time ago now, that so 1 is true and 2 is true over a characteristic 0 field. And from here, it's not so hard to show that if you take Floer cohomology between the Lagrangian associated to this picture and its image under some appropriate braid, then this tensor Q is Khovanov homology of the link closure tensor Q. So I plan to discuss, yes. It will kill all the torsion of all degrees. It's now known that the early known torsion in Khovanov homology was related to Z mod 2, but it's known that Khovanov homology has torsion of all possible Z mod P's if you look far enough in knot tables. And we don't know that these theories are the same integrally. Yeah, in fact, maybe I'll make, before I discuss two, a remark in the vein of Mina's question. So I said that combinatorially, Khovanov homology was built out of a Frobenius structure on H star S2. And if you inspect, somehow everything that happens, it turns out that what you really need to make Khovanov homology work is a two-dimensional Frobenius algebra. In particular, you can replace the algebra Z of X modulo X squared by Z of X modulo X squared equals 1. And you get a deformation of the entire Khovanov package, which is called the Lie deformation. Of Khovanov homology. So the resulting invariant of links is not interesting. Okay? So the Lie Khovanov homology of the knot closure of a braid is just Z2 to the number of components of the link. So this is a kind of stupid link invariant. But there's a spectral sequence associated to the fact that you have a deformation, and the spectral sequence has, in some sense, the most interesting information that anyone's got out of Khovanov homology to date. The spectral sequence from Khovanov to Lie Khovanov is interesting. Indeed, the tau invariant that Rasmussen used to show that Khovanov homology detects an exotic R4 is obtained from this spectral sequence. So that was somehow the first application of Khovanov homology to a question in low-dimensional topology that anybody cared about. So, so somehow, before going through the agony of doing this kind of thing, you might wonder whether or not a basic structure that's important in Khovanov homology is visible or has some analog in symplectic Khovanov. And it both does and doesn't. So I'm just commenting on this because it connects a little bit to Mina's question. Oh, hell's tea. In MSRI, we have these big fluffy sponges. They're much better. So, so the space Y2N is non-obviously given by taking S2 to the 2N and removing a certain divisor. This divisor is in the class 1111 in H2. So it's a divisor. It's a rather singular irreducible divisor. It's not like a smooth divisor. But for general reasons in Floer theory, there exists a deformation from doing Floer homology of any Lagrangians inside Y2N, if these are Lagrangians in Y, to computing Floer homology of L and K inside this larger space, where this deformation counts holomorphic disks that go through the divisor D. And it's expected, I mean, you know, I think I could prove, but it hasn't actually been written down, that this is again a stupid link invariant. It counts components only over, counts components of the link. If we apply it to our sort of symplectic Khovanov type setup in which we take this Lagrangian associated to these nested horseshoes and its image, so in the setting of theorem 2, well, this should be true for all coefficients. Okay. So, so the expectation is that on this manifold, the Bragg group action factors through the symmetric group. Okay. But over Z mod 2, well, Z mod 2 of X modulo X squared equals 1 is the same as Z mod 2 of Y modulo Y squared by setting Y equal to X plus 1. So the Lie deformation of the combinatorial Khovanov homology is completely trivial over Z mod 2. It doesn't change anything. The spectral sequence is just, it does nothing. Okay. So, you know, so this is one of those interesting points in which the theories seem to diverge in some basic way. The thing that looks like the natural analog of the Lie spectral sequence from many points of view definitely behaves differently to the thing that exists combinatorially with mod 2 coefficients. And you know, the formality theorem that we have is currently only true over Q, and specifically in mod 2, there are strong reasons to believe that, you know, this algebra would not be formal with mod 2 coefficients. Okay, so for the last 20 minutes, I wanted to say something about, you know, why this is formal. Well, no, something about why it's formal and something about how we show it's formal, which is sort of disappointingly different. I think I'm not actually going to reach annular Khovanov homology.
So the fact that the cohomology presumably also means that your homes will only agree with the Khovanov. I get that's the entire.
No, so part 1 is true over Z.
Oh, I see. Okay.
Um,
I guess it's surprising about that we do seem to recover all the sort of
Yeah, I mean, in the only known computation. So I think that it's almost certainly true that symplectic Khovanov homology and Khovanov homology agree over Z for all knots or all links. I think that's perfectly likely. I think that when you come to look at more subtle structures in the theory, that will probably cease to be true. So for instance, if you look at links invariant under an involution of S3, you can define a Z2 equivariant version of either Khovanov homology or symplectic Khovanov homology. And the most simple examples show they're different. So the theories are not somehow equivalent with all possible data. They're not equivalent as, for instance, Z2 equivariant theories for periodic links. My guess is that if you build the stable homotopy theories, they'll be distinguished by Steenrod operations. You know, that when you go deeper into the sort of bones of it, these sorts of discrepancy will appear in a way that they maybe don't if you do something as crude as just taking one Floer homology group. That's my expectation, but that's speculation. Okay, so let me say 3 things about formality. Okay, so the space Y to N is actually hypercalar. It's a certain quiver variety. And there exist complex Lagrangian submanifolds, K rho in the set of crossingless matchings, which are, you know, smoothly isotopic to the L rho I built before, but it's not actually known that they're Hamiltonian isotopic. Almost everything's not known. Yes, so, you know, this is a hypercalar manifold as a quiver variety. You know, it has a compact core given by thinking about it in one of its resolution complex structures. Those components of the compact core turn out to be complex Lagrangian submanifolds, each diffeomorphic to S2 to the N, and they meet in an intersection pattern which reflects the algebra I talked about before. But, you know, I mean, the Lagrangians I was writing down, which are given by pictures like this, right? They meet in isolated points, right? Or they meet, in some, like this one and the one for this cross-Sigma matching, right? They have sort of some finite set of intersection points, but the components of the compact core of a hyperkähler variety meet cleanly in interesting submanifolds. So these are not exactly complex Lagrangians. They ought to be complex Lagrangians if you brought the points together along the real axis. So this one, for the sort of the Platt crossingless matching, is complex Lagrangian, but the others aren't. They're probably Hamiltonian isotopic to it, but I'm not paid enough to check. Okay, so so the space Y to N is hyperkähler. So we have the following conjecture. So this is somehow due to me and maybe Paul. I mean, Paul Seidel and I formulated this as a question, and then I started believing it. I'm not sure if he believes it. That whenever you have this, a collection of complex Lagrangians in a hyperkähler variety, the direct sum of Floer cohomologies, the corresponding Floer algebra, is formal. And there's a kind of simple reason why you might think this is true. Probably complex symplectic is fine. I think complex symplectic, I suspect so, but these things are hyperkähler. So if I'm actually making a conjecture, why don't I kind of make life maximally safe? Okay. So let's note. Okay, so I'm in the situation that I have some hyperkähler manifold. It has, three Kähler forms with compatible complex structures I, J, and K, and my Lagrangians are, I complex and the holomorphic volume form omega 2 plus I omega 3 vanishes on them. So they're omega 2 and omega 3 Lagrangian. And I think about the following. I take something in the circle of symplectic forms spanned by omega 2 and omega 3. That's compatible with the complex structure that's the same sort of point, the same point in the circle of complex structures spanned by J and K. And now I think about the form, which is just given by kind of orthogonal rotation. That's to say, I change the coefficients of omega 2 and omega 3 by rotating in the circle by pi by 2. And the sort of easy observation is that this thing has type 0, 2 plus 2, 0 for J naught if I pull it back under any J naught holomorphic map. So if I take a Riemann surface with boundary, and I take a holomorphic map for J0 to X with boundary on the unions of these complex Lagrangians, then U star phi has no 1, 1 component. It's locally a 0, 2 plus 2, 0, 4. So that means that if I think about the pairing between, so somehow sigma defines a class in H lower 2 of X relative to the union of the LIs, right? Or U of sigma. On the other hand, phi defines a class in H upper 2 of X relative to the union of the LIs because it's in the span of omega 2 and omega 3, which vanish on the LIs. And phi U of sigma is 0. because I can't integrate a 2-0 or a 0-2 form over a Riemann surface. But if I think about it, and I just, I also have that the area of sigma, which is kind of omega evaluated on U of sigma, this better be greater than or equal to 0, because I have a J holomorphic map or J0 holomorphic map. But these two conditions are two equations in the values of sort of omega 2 U sigma and omega 3 U sigma, depending on this variable theta. And I can tune theta arbitrarily in the circle. So just by choosing theta generically, what I see is that U must be a constant map. So a more elaborate version of this argument has been written down more carefully in a paper of Solomon and Verbitsky. And what they show, what this argument, tidied a tiny bit shows, is that the A infinity structure on the Floer cohomologies of these complex Lagrangians is completely determined by constant maps. But constant maps are typically not generic, right? If 3 Lagrangians in your compact core all intersect, there's a moduli space of constants of the wrong dimension. And it seems very hard to prove why they don't contribute. So the A infinity algebra directs some HF Li Lj, if these are complex Lagrangian, is determined by constant holomorphic maps. Well, I'm saying that is what happens in all the sort of interesting examples. Yeah, if you actually find complex Lagrangian submanifolds, they're pretty rigid things. So you probably found them from some contracting C-star action or as components of a core of some quiver variety or something. Then they never meet transversely. They meet with, they meet in submanifolds. 3 will meet at a point, or indeed in a whole submanifold. So it seems hard to turn this into a proof that the A infinity structure is formal, but there should be a proof just in hyperkähler geometry that actually works out what the obstruction bundles over these moduli spaces of constant maps are and proves somehow for some consistent reason they don't count. And that should be work like the Deligne-Griffiths-Morgan-Sullivan theorem is work. This is not work. This is kind of fiddling, right? But there should be an actual complexification of DGMS that nobody's found. So this is why it's, why should it be true? Okay, okay, let's suppose we've given up on hyperkähler geometry as difficult. And we go back to the arc algebra and we think, well, let's try and prove formality just in this case, which is after all fairly tied to representation theory.
So say the Lagrangian goes up there.
The one.
Example on the top board, right? There would be some degenerate but not.
So, I mean, I'm not sure which Lagrangian.
The one up there is sort of doubled up.
So there I was. So if I take any of these crossingless matchings, this will be a Lagrangian in Y2n that is complex Lagrangian only if I take this thing, in which the arcs at which I join my pairs of points lie inside the real line. If I take a collection of arcs that lie inside the real line, inside the base of the Milnor fiber, then I get an honest complex Lagrangian.
I guess you wouldn't like that one, but it would intersect.
But that's the thing. If I try and do that with this, right, now I'm in trouble. Right? The vanishing cycle construction doesn't work. These things all have descriptions in terms of iterated diagonals in S2 to the 2n, in which you can see that they have nice intersections. That's somehow the right picture. But it's not completely trivial that the pictures you get from parallel transport in A to N in products of Milnor fibers and that sort of compact core are actually the same. Okay, so part 2 would be deformation theory. So since I put annular in the title, I will say 3 minutes about this because it will at least connect to where annular Khovanov comes in. So if A is an algebra, I can study formal deformations of A. And they're governed by Hochschild cohomology. So this is a cohomology of a complex. In which the sort of generators of the Dief cochain group are given by kind of products of arbitrary tensors from tensor powers of A to the D to A with certain gradient shifts. And then there's something called the Hochschild differential that I won't write down. Okay? Classical deformation theory is usually actually governed by HH2. Okay? But and there's a version of this also for A infinity algebras. Okay? So you could think of, my arc algebra, which is like Khovanov's arc algebra, but with some additional mu k's that we don't really understand as a kind of formal deformation. Of the arc algebra. And so if you understood all formal deformations, maybe you could prove this deformation was trivial just by knowing what they all were. But there's a problem, which is that we don't. People have some understanding of the Hochschild cohomology of the arc algebra, and it's vast and complicated. But we haven't actually used all the structure available to us. So everything we were doing started with the fact that the 4-dimensional Milnor fiber wasn't just a symplectic manifold, it had this God-given map to C, which let us define these Lagrangian matching spheres. They didn't just use the 4 manifold, they really used this projection. And this induces a map which you might think of as the sum of the different copies of pi on the Hilbert scheme of n points in xp to C, which remember contains our space y to n. So we have this natural map pi given by taking an n tuple of points in the Milnor fiber and just adding up their projections. And it's a fact that pi is a Lefschetz vibration. It has some critical points at infinity. Let me ignore that. And so we can consider the Fukaya-Seidel category of pi. Which includes some non-compact Lagrangian submanifolds. And it's a theorem that Cheuk Yu Mak and I proved maybe 3 years ago or so, that this Fukaya-Seidel category is actually equivalent to the derived category of modules over a certain extended version of the arc algebra. We call it HN2N extended, which was introduced by Katerina Stroppel. This is Stroppel's extended arc algebra. So, I won't say anything about this to say that it contains Khovanov's arc algebra. Okay, so it still has exactly these Lagrangians associated to these crossingless matchings, but now it has some additional Lagrangians, and you add their Floer groups as well. And Stroppel has a beautiful conjecture, which unfortunately we were not able to prove, which says that the second Hochschild cohomology of the extended arc algebra is isomorphic to the second cohomology of the space Y2N, at least if you work rationally. So this is, she might even believe this integrally, but so if this was true, you'd kind of be done, okay? Because what would this say? It would say we're interested in some deformation of this collection of Floer cohomologies associated to compact Lagrangians. But our space also contains all these non-compact Lagrangians. So whatever we get out of geometry is really a deformation of this bigger algebra, right? This is what we see cohomologically. Whatever the infinity structure is, it's deforming this as well as the arc algebra. So our deformation of the arc algebra comes from a deformation of this. But the only deformations of this are the things that you get by changing the symplectic form on the space. And if you deform the symplectic form, some of your Lagrangian submanifolds disappear. Okay? But none of our Lagrangian submanifolds disappear. All the objects are actually there. So if you understand that all the formal deformations come from changing the symplectic form, we must have the trivial deformation. So if this was true, this would imply formality over Q. And this is not something as general as the hyperkähler story, but this is something that somehow a sufficiently good algebraist ought to be able to prove. I mean, Katerina proved it up to maybe 8 strands or something just by being a monster. But, she also said that if somebody paid her enough, she could prove it. But, I mean, they don't pay me enough, I'm not going to pay her enough. Okay, so these are 2 reasons for thinking ahead of time that the symplectic version of the arc algebra should be formal for kind of both good geometric and representation theoretic reasons. Okay, and that's really the heart of why symplectic geometry can recover Khovanov homology. But we don't actually have access to those proofs, so we had to do something different. So is it okay if I talk for 10 more minutes?
Yeah, we're flexible with time.
How did the audience feel? Do they not leave because you paid them? Okay, so.
Question: if you get Stroppel's algebra from your at the moment, Lagrangians, right? It's not some magical. You don't use the.
So to prove this, one of the definitions of Stroppel's arc algebra, the extended arc algebra, is actually as a quotient of the ordinary arc algebra on twice as many strands. And we prove that the endomorphism algebra of a particular collection of objects here is given by the same quotient. Maybe it's actually just worth commenting for a moment in the context of this theorem that almost always in the setting of the Fukaya-Seidel category of a Lefschetz vibration, usually you would study the Floer theory of the Lefschetz thimbles. Okay. And in this case, this is not a formal A infinity algebra, even over Q. So that's a bad idea because, you know, once you've found some A infinity structure, if you don't have some a priori reason for knowing how far it's going to go, you're basically in a mess, right? But somehow either the representation theory or an appropriate kind of C-star action will pick out for you a different collection of objects that are not just the compact objects. They include some thimbles and some things that are kind of mixed, whose endomorphism algebra is formal because they're the projectives in this algebra, this derived category. So somehow, but you know, if I gave you a general four manifold with a map to C, you always get a Lefschetz vibration on some piece of the Hilbert scheme. And in general, we would have no idea how to compute this beyond the cohomological level because we wouldn't know how or if there was any kind of reasonable formal collection of generators. So that's really something that, again, just as in the arc algebra, we kind of used Khovanov's combinatorics to guide what we should build in the geometry. Here we take a collection of objects that Katerina tells us to look at, and we prove their endomorphism algebra is formal over Q. But yeah, the objects that you have to look at don't satisfy the usual conditions you want in a non-compact symplectic manifold. So to prove this, you have to do quite a lot of work. They're not so-called cylindrical at infinity Lagrangians. Okay, so what's the actual argument? Let me say a tiny bit of generality, and then I'll say something specific. So let A be a graded algebra. Okay. Or graded by the non-negative integers. Okay. So then I can define what's called the Euler vector field E from A to A, okay, which multiplies the grading I piece of A by I. And if this is a graded algebra, the fact that AI times AJ lands in AI plus J under the algebra product says that E in CC1 AA is a Hochschild cocycle. Okay, so remember, I said that what this looks like, it's some vast product over homomorphisms from D tensor products to A with some grading shift, right? But this is something which is zero except in the D equals 1 piece where it's just a homomorphism from A to A. Okay, and it preserves the grading. It sends AI into AI. It just multiplies the elements by some number, right? So E is living in here as something very boring. In this infinite product, it lives only in 1 piece. And it's just a lemma in algebra. I mean, just like 6 months of my life. But it is just a lemma in algebra that an A infinity algebra, A, is formal over Q if and only if there exists an element in CC1 AA, which is a cocycle, so it defines an element in Hochschild cohomology such that it acts on the cohomology of your algebra as the Euler field. But, you know, the definition of the Hochschild complex for an A infinity algebra, the differential involves all the A infinity operations. This is not something you're checking on the algebra. This is something that's natural at the level of the A infinity algebra. So the upshot is we want to understand HH1. Okay. Yeah, and so if X is a reasonable symplectic manifold, well, there are maps from the cohomology of X to the symplectic cohomology of X. So this is some version of Floer cohomology involving dynamics near infinity. So I'm imagining that X is non-compact, mapping to Hochschild cohomology of the Fukaya category of X. So, and well, there's a cousin of the Fukaya category called the wrapped Fukaya category. And this map is actually an isomorphism in great generality, mostly by work of Ganatra, but others also. So the idea is that we should be looking at something that comes from infinity in the symplectic manifold. But to actually get hold of this geometric invariant, you know, if I hand you a manifold like this curly Y, we have no idea what infinity looks like. We don't have any good control of that. Okay? But everything we were doing with Y came originally from these Milnor fibres. Okay, and so, you know, so what we can do is write down a class in sort of HH1 of, you know, the Fukaya category of the Milnor fiber, and then generalize the construction to the space Y. And I mentioned a while ago that
So just one question. You have this Fx or Wx, do you allow stop?
I mean, so if you want to allow stops, it won't be symplectic. Oh, I mean, you know, that changes the definition of symplectic cohomology because it changes the class of Hamiltonians. Right? So there's a version of symplectic cohomology that takes account of a stop. Then it would be, you know, a conjecture but not a theorem that was isomorphic to the Hochschild cohomology of the corresponding partially wrapped category. But in the end, I really want to apply things to compact Lagrangians for the arc algebra. So. Okay, so I should be writing down some class, you know, in Hochschild cohomology of this object, right? And it should have something to do with infinity. And a while ago, I mentioned to you in the context of this Lie spectral sequence that if I compactify a symplectic manifold, so if I have X and I sit it inside X bar, which is X union a divisor D, I get a deformation of Floer theory by counting disks that go through the boundary. And deformations correspond to classes in HH2. So I want to do something that involves infinity, which I might think is going to give me an HH2 class, but I'm looking for an HH1 class. So I want to do something that somehow cuts down the dimensions of my moduli spaces by a real number, 1. Okay, which is something sort of you might not imagine that you want to do if you're used to thinking about affine algebraic geometry and projective compactifications and the like. So what we actually do is the following. So we compactify XP just vertically to the thing that has sections over naught and infinity added into all the fibers to make them kind of look like P1s. Okay, and so now the singular fibers not affine conics, but they're unions of 2 P1s. And so our Lagrangian submanifolds were things that used to live over this. Now they live here. Okay. This is maybe how it lies inside some particular fiber. And I count holomorphic disks which schematically look like the following. So they have boundary on my Lagrangian L. The origin goes through my divisor D. If I was just doing that, I'd be doing a kind of standard deformation theory problem. I'd be adding in disks that go through infinity. But I fix, in addition, a push off of the divisor. Okay, let's suppose that exists. In this toy case, it does. So I have a second copy of the divisor running parallel to it. And I count this, well, if a disk goes through D, it will also go through D prime. They're homologous, right? That's an intersection number thing. I mean, let's suppose we do that, or you control the high codimension locus where it isn't. And then, but instead of just, if I send the origin to D, I'll hit D prime somewhere, but I insist I hit D prime on the real line between the center of the disk and the point 1. So this is a real codimension 1 condition on the moduli spaces I would usually think about. Okay, and instead of just thinking about things with one Lagrangian boundary, well, I could have had lots of different Lagrangian boundary conditions. And then this is exactly the kind of thing that I would see in the Hochschild complex, a long tensor product of morphism groups, a single output, and some constraints to do with the geometry of my symplectic manifold at infinity. Okay? So it's a kind of not so difficult exercise to check that this is a non-trivial element of HH1 of the Fukaya category of the Milnor fiber XP. And then there's a certain amount of work in taking, a similar definition on this open part of the Hilbert scheme, Yn. But once you've made a definition, which involves a certain amount of pain because the space is complicated, somehow checking that it's non-trivial, well, the Lagrangians you really care about live in some nice open part of the manifold very far from the diagonals. You can compute all the holomorphic curves you ever need to count for that by some product argument, and it all comes down to this picture. Okay, so similarly, on any given Lagrangian in the Hilbert scheme, its self-Floer cohomology is just a tensor product of copies of this picture. So if you hit the Euler field on this, well, at least on some large part of the arc algebra, you know you'll be the Euler field, namely on the parts HF L, comma L for a fixed L. Then one needs to do some work to really show it's the Euler field altogether and hence prove this formality. But I'm tired, so you must be shattered. So let's stop there. Thank you for your attention.
And geometrically, the corresponding grading is what? The grading on the algebra.
So the point is that on the actual arc algebra, this grading is completely uninteresting because the Euler field doesn't induce an interesting grading on an algebra. It multiplies the ith piece by I. What's then true, though, is that if I have an element in HH1 of some A infinity category, right, then this includes in particular an endomorphism of every pair of objects. This is kind of the length one part. The thing that in this long product expansion is the length one part of this. So if B is in CC1, this was meant to be a product over hom A to the dA over all D greater than or equal to 0. Right? So if I take the D equals 1 part, that's an endomorphism of the algebra. In the setting of a category, that's an endomorphism of every morphism space. So now what I can do is take the generalized eigenspace decomposition for this endomorphism. But a priori, that's just a grading by elements of the algebraic closure of the field, not, for instance, the integers. So a student of Mohammed's checked, but somehow not by methods internal to symplectic topology, that the bigrading you get from this HH1 class is Khovanov's bigrading. But that was sort of by checking compatibility with exact triangles and reducing to some specific cases. So there's no kind of internal to symplectic proof that it's a sensible bigrading.
So if one for some reason knows that there's no higher UK, then one is not like that's a check the fixed automatically follow.
Sure. But if you also have no mu1, right? If there's only mu2, then that by definition means you're formal, right?
And here also here, so Seidel-Solomon has this BV operator stuff and reduced the degree by 1. Is that related to your construction from HH2?
So that's not related to going from HH2 to HH1. So so I would say that there's this map from H1 of X to SH1 of X. Okay, and let's suppose we're secretly in some situation where we know that this is HH1 of some flavor of the Fukaya category. Okay? So you can use any class here to try and bigrade morphism groups. On the other hand, it's completely classical that if your manifold has non-trivial H1, you can just use kind of winding number type arguments to bigrade Floer theory. So they somehow specifically wanted to give conditions on a class in HH1 that would tell you that it didn't come from here, so that the symplectic geometric consequences they drew were non-trivial. Okay, and there is this BV operator delta on this, which vanishes on the image of this map. Okay. So they used the fact that they started with something that satisfies this, now in SH0 of X, to prove that their class B didn't come from H1, so what they were doing couldn't have been done by topologies. This is, of course, connected to properties of C-star actions on the mirror, but this in itself is not going to, this doesn't help you per se prove formality, as far as I know.
So it's not equivalent as depending on some condition of B0 equals
No, that's a sort of infinitesimal equivariance condition, which I did. No, and in fact, in the geometric setting, it's not true that B0 restricted to L is 0. What's true is it's a boundary of something, and you have to actually choose this. So yeah, right. If I'd been more careful, I would have said that this data actually gives you an automorphism of not quite morphism groups, but morphism groups where you equip these Lagrangians with a little bit of extra structure, which may or may not exist, but always exists if the Lagrangians have H1 equal to 0, which was our setting. So yeah, so the BV operator is kind of useful for a different direction of symplectic applications, but I don't think it's specifically useful for formality.
In your setting, the differential would add
So in our setting, if you take the basic crossingless matchings, then you can arrange, even in this nice picture in which they intersect in finitely many points, that all the points live in a single mod 2 degree. And hence the differential on the algebra is trivial for sort of easy reasons. Yes.
And the product is not difficult to compute?
The product is not easy to compute, and to pin it down over Z was a nightmare. Yeah, so in fact, the product's hard to compute.
So how do you do it? Do you have complication?
No. So we use the fact that by an inductive argument over the, there are these basic Lagrangian correspondences that relate these spaces Y to N for different N's. So using that, you can show that although you don't know these look like the kind of natural complex Lagrangians, for any given pair, you can make L rho intersect L rho prime cleanly in a copy of S2 to the number of circles that you would expect. So for Lagrangians that meet cleanly, you then know that the Floer cohomology of this pair is naturally isomorphic to the cohomology of this locus. Okay. So now, when you have 3 of these Lagrangians, we proved that if one of them is this one, you can actually find a local model. You can actually prove that the Floer cohomology of the triple is given by the Floer cohomology of the 3 in some local plumbing model. And that's to say, you can really make the 3 Lagrangians live in the cotangent bundle of 1, like the conormal bundles of 2 submanifolds. And in that case, you can completely understand the Floer product as a kind of convolution product on homology. In general, 3 Lagrangians don't have a plumbing model. Any 2 Lagrangians that meet cleanly always have a universal local model. But there's a sort of so-called Maslov triple index for 3 Lagrangians that mean that's not true for 3. So we proved that the products where one of the inputs was this determines the whole algebra by a complicated inductive argument. That was actually the single piece of the project that took us the longest, just to pin down the actual algebra. Although in the end, the proof is, it doesn't use anything deep, but we didn't know how to prove it directly.
So this is which paper?
This is the last paper that Mohammed and I wrote. No, sorry, this is the paper that Mohammed and I wrote on Khovanov homology as Floer cohomology. So there's a long section of that paper that just pins down the actual multiplicative structure in the symplectic arc algebra as an algebra over Z, so with signs. Yeah, but
I know that I proved that you get a multivariate.
yes.
Did you reprove it here or you did not do that?
We didn't need to, so and we certainly, I mean, in some sense, the most delicate part of proving that it's a not invariant is to prove that this Lagrangian is Hamiltonian isotopic to this Lagrangian. Of course, that's stronger than you need. I mean, you only need that they're isomorphic in the Fukaya category. That you could, in principle, prove by actually writing down some explicit holomorphic annuli. But it's easier if you know that they're Hamiltonian isotopic to use that. So in all the later papers, we use this constantly.
And you actually, maybe I missed. So, in relation to annular homology.
Yeah, I didn't reach it. Somebody asked about why don't you just take the Floer homology of the symplectomorphism. So if you have a braid beta, you can consider the induced symplectomorphism on the Hilbert scheme of I points for any I. And annular Khovanov homology is given by adding up those Floer cohomologies from I is 0 to n. So it lives somehow on, the spaces y naught up to yn, where actual Khovanov homology lives on the space y to n. That's it, kids. You can go home.